Hey, editor Dr. K here. This first question is not complete, and so if you want to skip it, it's not going to be on the exam, so you can jump ahead. I'll put the timestamp on the screen here so you know where to jump to.
All right, so we're going to work through these problems pretty fast. Hopefully, you've already tried them on your own, and this is not your first time seeing them. And really make sure that you've tried and given it a really good first effort to get through these. This first one is just a general stoichiometry problem, but it's also combining some other stuff here as well. Our goal here is to figure out how much charcoal it's going to take. Okay, I can't use that. But how much charcoal is going to take to heat up this steak. So there's a couple things that we need to do here. The first is that we're going to need a balanced chemical equation. So we're given that actually in words: carbon dioxide, carbon monoxide, heat, oxygen, and the charcoal. So charcoal, and we're told here that charcoal is made almost entirely of solid carbon. So if our charcoal is carbon, that's going to react with oxygen, which is O2, because it's diatomic, to produce carbon dioxide plus carbon monoxide. This is a little bit contrived because it's a problem that I made up. So to get this all balanced, we have one carbon on our reactant side. We're going to need two carbons because we have two carbons in our products, but we have three oxygens in our products. So we're going to have to do this 3/2 trick, and then we're going to multiply everything by 2. So we're actually going to get 4, 3, 2, and 2. And so those will become the coefficients here. And that'll give us a balanced chemical equation. Now, that's only part of it because we're also producing, this is delta H, producing 30, actually this would be negative 34 kilojoules. And then that's going to be negative 34 kilojoules per every 4 moles of carbon or charcoal that's burnt. So this is an amount of heat that's being generated, but we don't know how much heat we need yet. We know some other stuff though. We know that we have a 9-ounce steak, and we're trying to heat that to 63 degrees C. And it looks like I forgot to add this little bit in here. We actually need the heat capacity of steak. I wrote this down somewhere very recently. It's 2.76 joules per gram degree C. That's unfortunate. So you might have looked up a different value for that somewhere else. The other thing that we're going to have to do is take this 9 ounces of steak and convert that into grams. So you might have used a table to look this up, like the one from the unit analysis worksheet. So, well, 1 ounce is going to be 28.3494 grams. So if we convert this, 1 ounce is 28.3495 grams, which means that's going to be 255.146 grams of steak. Okay. And so we want to heat that up. Oh, I'm missing another piece here. If we're assuming the steak is at 0, which would be frozen, it's probably not going to be at 0. So we need what's like a refrigerator temp at in degrees C. 4 degrees Celsius. Okay. So need to add to this from 4 degrees C. So now that gives us everything that we need. So some of this stuff I needed to include this heating it from 4 degrees C. This is the specific heat capacity. a steak. It's actually beef loin, but it's close enough. So you would need those things to solve that problem. The rest of it you could have figured out. Here now we need to know how many joules it's going to take to heat our steak. So Q equals mc delta T. So Q is what we're looking for. M is the mass of our steak, 255.146 grams, times the specific heat capacity, which is 2.76 joules per gram degree C, times the change in temperature, which will be our final temperature, which is 63 degrees C, minus our initial temperature, 4 degrees C. So 255.14 times 2.76 times 63 minus 4. So Q equals 41,546.9976 joules. And because now we're going to take this number of joules, we can relate that back to our chemical equation here. But that's in kilojoules. So we have to convert this to kilojoules. So 1,000 joules is 1 kilojoule. So that's going to be 41.547 is probably enough sig figs, kilojoules. Okay, so now starting from this 41.547 kilojoules, we need to essentially do stoichiometry here. And now from our chemical reaction above, we know that we can get 34 kilojoules for every 4 moles of carbon. And that let's see, how many grams of charcoal? So then now we need the mass of carbon. So 12.01 grams carbon for every 1 mole of carbon. So 41.547 times 4 times 12.01 divided by 34 would give us about 58.7 grams of charcoal. Roundabout. Now, the thing, of course, is that most of your heat when you're cooking anything does not go directly into the thing that you're trying to cook. It ends up in the room or going around whatever you're cooking. So I guess I'll give pause here for just a few seconds. Now, this first question is not going to be on this upcoming exam. Okay. Again, hopefully you've tried these. If we want to draw an orbital diagram for sulfur or sulfide, because it's the ion, that shows the relative energy levels. So these orbitals have different energy levels, and the reason that we're filling from the bottom to the top, so this is going to be the 1s orbital, this is the 2s orbital, that's the 3s, or sorry, not 3s, 2p orbital. And periodic table is very helpful here. So this is going to be 3s and then 3p. Now notice that this is S2 minus. So what that means is we can look at the periodic table, and sulfur is in group 6a, which means that sulfur, no charge, what is it up there? No charge, would have 6 valence electrons. But because we have a 2 minus charge, that means that we have to add 2 more electrons. So this is going to be 8. So 6a would be 6 electrons plus 2 electrons will be 8 electrons. And we can just fill those in from lowest to highest. So 1, 2, 3, 4, 5, 6, 7. Oh, sorry, 8 valence electrons. The total number of electrons that sulfur has is 16. Excuse me. So 8 valence electrons, so that would be the valence electrons, which would just be, these are the valence orbitals. They're the highest principal shell number. So if we were filling in up there, then it would be just that. But if we're doing all of the energy levels, then we would have to take this, the fact that sulfur has 16 electrons total. So all of this is valence. 16 total electrons plus the 2 electrons to give it that 2 minus charge. So 18 electrons total. So let's start over here using that in mind. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And that makes sense because with 2 extra electrons, now sulfur gets 8 valence electrons, which is a full octet. So same thing here applies for gallium. And again, we can get the total number of valence electrons from the periodic table. And instead of using the group number here, we're going to use, which would just give us the valence electrons, we're going to use the atomic number. So gallium is atomic number 31, which means that neutral gallium would have 31 electrons. But this is gallium 3 plus. So gallium 3 plus will have 3 fewer electrons. So this is going to be 28 electrons. Now I'm going to start lower because we've got more orbitals to write in here. So this is going to be 1s, 2s, 2p, and see that's a little bit higher, so our energy is here. And then 3s, and then 3p. And then this is where things get a little bit out of order. We'll go 1, 2, okay, we'll go 4s. And then a little bit higher than that will be 1, 2, 3, 4, 5. That's 3d. And we've got 28 electrons to fill in here, so we start at the bottom. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. I think I counted that correctly. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. Nope, I was off by 1. And that makes sense. So these last two, instead of being paired up, would be like that. So there's the orbital diagram for gallium. Here in number 3, it's a little bit weird. So let's do the valence electrons here, starting with argon. Or I guess they're not the valence electrons, but starting with argon, if we're doing chromium. Chromium will have 4s2, and then 3d. Chromium is 1, 2, 3, 4. 3d4. So if we do our 4s orbital, and we do 3d, what happens here is, I guess I said we don't need to show the relative or energy levels, but that's okay. The normal way to fill this in would be do 4s, 1, 2, and then 1, 2, 3, 4. And you would stop there. But as we're told here, or as I told you guys in these instructions, it maximizes the number of single electrons. So actually, one of these 4s electrons gets moved into the 3d. And this is especially stable with all of those orbitals being filled with all electrons in the same spin. All right, so Lewis structures here. I tried to pick some weirder ones. So AlCl3, aluminum, it's going to have 3 valence electrons. Sulfur, chlorine, it's going to have 7 valence electrons, but that's going to be times 3. So we're going to have a total of 24 electrons here. So we'll do aluminum, chlorine, 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 and then that uses up 6 of our electrons. So it leaves us with 18 left. So it's 2, 4, 6, 8, 10, 12, 14, 16, 18. And generally speaking, this is the correct Lewis structure. Even though aluminum does not have a full octet, boron and aluminum can have incomplete octets. So is this going to be polar or nonpolar? The first thing you should look at is what is the shape of this? Now this one, if you look it up, it's going to have aluminum, going to have 3 electron groups, and they're all bonding groups. So that makes it trigonal planar. And if it's trigonal planar and all of the groups are the same and there are no lone pairs on the central atom, this is going to be nonpolar. Now if we move over here, this is nitrate. So nitrogen, oxygen, right? Nitrogen has 5 valence electrons, oxygen has 6 valence electrons. Multiply that by 3, and then we also have a negative charge, so that's going to be 1 more valence electron. So we essentially get 6 times 4, 24 electrons. Do our nitrogen, sorry, like so, right? Skeletal structure, minus 6 electrons again, and this will give us 18 left over. 2, 4, 6, 8, 10, 12, 14, 16, 18. Now, nitrogen is not happy with, it's not okay with an incomplete octet. So we'll take some of these electrons and we'll share them into there to make a double bond. And then because this is an ion, we'll add the charge up there. So now we can look at this. Nitrogen, 3 bonding groups. So this is also going to be trigonal planar, and it will also be nonpolar. Now, the thing that I didn't add on here is about resonance structures. So if we back this structure up a little bit to this point, we could have drawn this and pulled these electrons from any of these oxygens, and that would give us 3 equivalent structures. So a separate structure for each of those situations. So those are all equivalent, and because of that, any of those would be acceptable as a single structure, but should also be drawn out if resonance structures are asked for. Oh, I'm sorry, that's the next question. So the resonance structures, this is just the first one that we drew out up there. And then the second resonance structure, we would take those electrons from somewhere else. Something like that. And then the final option here would be to take them from that last one over there. So these 3 structures are the resonance structures of nitrate. Okay, these are probably the more challenging questions. And I think the best way, the easiest way to explain this is to draw out the Lewis structures for each of these. And we're looking for patterns here. So just real quick, draw out these structures. So that's that. Oxygen, 2 hydrogens. Okay, so we've got these 3 structures. So what do they all have in common? They don't all have the same elements. They don't all have the same number of bonds. But if you were to look at the table for figuring out the shapes of these would all fall into the same category of having 4 electron groups. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So same number of electron groups, same electronic configuration. They're all tetrahedrals. Tetrahedral electron configurations, because we have 4 electron groups on each. So with that in mind, if we then compare the Lewis structure of oxygen, so now the molecular structure, molecular configuration, same thing, is bent for water. But for SO2, if we draw out this Lewis structure, oops, S in the middle, it's also bent, but it's a little bit different. So the electronic structure is different because here again, this is 4 electron groups. To do this capitals, huh? Electron groups. This is only 3 electron groups. Okay. And because of that, the angles between each of those electron groups end up being different. So here, this is bent, but its electron configuration is going to be trigonal planar. Or not electron configuration, electronic structure. And so it's going to have a bond angle of 120 degrees. Let's see, 120 degrees. Whereas this will be something closer to 109.5 degrees between each of those. So what makes a molecule polar? A molecule is polar if there's a difference in electron density. So let's look at one simpler structure here. So there's a different so if one side of the electron of the molecule, one side of the molecule has a different electron density. So one side is more electron dense than the other, which means that one side has more electrons than the other side. A simple example would be something like this: hydrofluoric acid. Each of these are electrons. And even if we were to compare just the bonds, the electrons are mostly around the fluorine. So less electrons, more electrons. And when you have simpler molecules like this, you can look at the polarity, right? When we have just 2 atoms that are bound together. For other things, I'll try and draw this. Let's do NH3. So this is going to have a trigonal pyramidal shape, and it has this lone pair here, and that lone pair is made of electrons. So this side is going to have less electrons. This side is going to have more electrons. And so that makes this polar. So there are poles that have differing electron densities. So how many liters of carbon dioxide are produced when 237 grams of propanol is burned at 0.908 atmospheres and 9 degrees Celsius? So we got to write a balanced chemical equation here. And this is a harder question partly because of this. Still accidentally undoing sometimes. Excuse me. This is actually a Chem 1 question, but you could answer it in Chem 20. So we have propanol, and propanol is being burned, which means that it's reacting with oxygen, and it's forming carbon dioxide plus water. That is what happens when you burn things that are made out of carbon. You get these products. And to balance this, we're going to have to do a couple things. So we need 3 carbons, and then it's easy to miss this, but there's hydrogens here and there's a hydrogen there. So that's actually 8 hydrogens. So this is a 4 to make the hydrogens line up. And now that's 6 oxygens, 4 oxygens, so we can just put a 5 here. Sorry, can't just put a 5 there. Because on this side we have oxygen here, and we have oxygen here. So what we would do if we only had the oxygens in the one spot is we would just say, oh, that could be 5. But we actually have 3 total oxygens on this side. And one way to think about this is that this is 1 oxygen. How many more oxygens would we need here in this spot? Highlight it to get back up to 10. So we would need 9 oxygens there. But we can't do 9 oxygens. We have to do 9 over 2 because it's an even number. And then we do this trick where we multiply everything by 2. So this will become 2, 9, 6, and 8. Get rid of all that stuff. So there's a balanced chemical equation. Now we can start out with this 237 grams of propanol, C3H7OH, and we can start out by doing some stoichiometry. So the goal here for any problem like this, because it's asking like how many liters of CO2 would be produced, that's a different compound than propanol. So we need to convert from one compound to another compound. That means we're going to use stoichiometry. That means that we're going to use this balanced chemical equation. And we're going to use this to figure out how to make that CO2 from, you're going to figure out how to make that CO2 from propanol. And we're going to need then the molar mass because these are mole ratios. So 2 moles of propanol will make 6 moles of CO2. And so to do that, we're going to have 12.01 times 3. So that's carbon, hydrogen, oxygen, 1.01 times 8. And 16.00 times 1. This will give us our molar mass. So that's 60.11. So 60.11 grams of propanol, C3H7OH, is 1 mole. So that's the mass of just 1 mole of propanol. So we can use that to convert our 237 divided by our 60.11 gives 3.94. Actually, before we even do that, we can put another step in here. Because now we can take our ratio here, 2 moles of C2H7OH to 6 moles of CO2. And that's our mole ratio that'll let us convert those numbers. So still starting with 237, and then multiply that by 6, divided by 60.11, and then divided by 2, and that'll give us 11.828 moles of CO2. Now, we're not quite done yet. Again, we're looking for CO2. We can take our moles now, and we can use PV equals nRT to figure out how many liters of CO2 will be made. Now I'm going to rearrange this before I even plug numbers in. And so we can take our 11.828 times, so write this in, this is moles, times 0.0821 atmosphere liters per mole Kelvin, times, our temperature here. So our temperature is in degrees C. So we got to add 273.15 to that, 282.15 Kelvin, over the pressure, which is conveniently already in atmospheres. So 11.828 times 0.0821 times 282.15 divided by 0.908. This will be 302 liters of CO2 is the amount of gas that you could make. So I'll give you a little zoom out on that real quick. Give it a few seconds. Okay. Now, a hot air balloon is filled with air at a temperature of 20 degrees C, and the volume of the air inside the balloon is 2 times 10 to the 7 liters. If the temperature of the air inside the balloon is increased to 70 degrees C, what will the new volume of the air inside the balloon, or what will be the new volume, assuming that pressure remains constant? So, pressure remaining constant is a hint that we need to use Charles' law here. So if we're starting with 2.00 times 10 to the 7 liters over 20 degrees C, but converted into Kelvin, it's going to be 293.15 Kelvin, equals whatever our V2 is, over 273.15 plus 70, 343.15. Now you can take our 2 times 10 to the 7 divided by 293.15, multiply that by 343.15. Gives us another big number, but it's 2.34 times 10 to the 1, 2, 3, 4, 5, 6, 7. Okay, times 10 to the 7 liters equals V2. So that's the new volume inside the balloon. This next part of the question is where things really get tricky. So in this next part, we're asked about the density of the balloon. So the density of the balloon has to be less than this number to fly at 1 atmosphere. We're also told the composition of the air and asked what is the density of the hot air balloon and will this balloon be able to fly? So the first thing that we're actually going to do is we're going to be using some numbers from our previous question, specifically this temperature and the number of liters that we calculated. If we do that, pressure, volume, moles, R, temperature, our pressure is now 1 atmosphere. The volume is 2.34 times 10 to the 7 liters. N is what we're actually going to look for. R is 0.0821 atmosphere liters per mole Kelvin. And the temperature will be 343.15 Kelvin. Now, why do we want to find moles? If we want to calculate the density, we need to find grams. And if we want to find grams, then we need moles. So if we can get moles, then we get to grams, as long as we have the molar mass. So we also need molar mass. And that's where the composition of the air comes in. So if the air is 70% N2, 29% O2, and 1% CO2, then that's telling us that the air's molar mass is going to be a combination of these three facts. Now we can calculate the molar mass of each of these, right? 14, or see the N2 is going to be 28.02. Oxygen is going to be 32.00. And CO2 is going to be 12.01 plus 16 times 2. It's going to be 44.01. And what we're going to do actually is multiply by these percentages and then divide that by 100. This first one is 19.614. This next one is 29 times 32 divided by 100 equals 9.28. And then 1 times 44.01 divided by 100 equals 0.4401. And then if we add all of those together, we get 29.3341 grams per mole as the molar mass of air. Now, we've already got our PV equals nRT up here. PV equals nRT. If we rearrange that real quick, we'll get PV over RT equals N. So 1 times 2.34 times 10 to the 7 over 0.0821 times 343.15 Kelvin. That'll give us N. So 2.34 e to the 7 divided by 0.0821 divided by 343.15. And don't be scared, it's a big number, but that's okay. This is going to be 8.3059 times 10 to the 1, 2, 3, 4, 5 moles of air. And now we can use the molar mass of air that we calculated. So 1 mole of air would weigh 29.3341 grams. So multiply by 29.3341. That's going to be 24, or sorry, let's do it this way, 2.436 times 10 to the 1, 2, 3, 4, 5, 6, 7. That's grams. So I'm going to move down here, 2.436 times 10 to the 7 grams divided by our volume. Now our volume up here is in liters, so we need to convert that to milliliters. Let's see, let's do it over here. So that's 2.34 times 10 to the 7 liters. Now 1 liter is 1,000 milliliters. So 2.34 e to the 7 times 1,000, that's 7, will be 2.34 times 10 to the 10. So if we take our 2.436 e to the 7 divided by 2.34 e to the 10, we get the density of gas, this is in milliliters, the density of gases of the gas in the balloon, the air in the balloon, 0.00104 grams per milliliter. Now, will the balloon float? If something is less dense than the thing that it's going to be floating in, then it will float. So 0.00104 is, in fact, less than 0.00121 grams per milliliter, which means the balloon will float. Okay, I hope that's helpful. I hope that these challenge problems got you to think more about how these things work together and using some of these calculations together.